Exercise 28. Here we have to prove that a group G is cyclic if and only if there exists an onto homomorphism from the additive group of integers to G. If and only if, that means we have to prove two implications. So any one of them can be proved first. So let us start by assuming that there is such a homomorphism. Let f from Z to G be an onto homomorphism. Our aim is to prove that G is a cyclic group. Let small g be the element f of 1. F of 1 of course will be an element in G, and we are calling that small g. Now our aim would be to show that this capital G is in fact generated by this element small g. So that way it will be a cyclic group. So what do we need to do to prove that thing? Namely, that if we take any element of G, then that should be an integral power of this small g. Okay, so let's take any arbitrary element in capital G. Let H be any element in G. Now since our function f is onto, so H is the f image of some integer. Since f is onto, H is equal to f of n for some integer n. Okay, but since f is a homomorphism, f of n is n times f of 1, and this is true even when n is a negative integer. Okay, this is a property of homomorphisms. So H is n times f of 1, that is n times G, and of course you have to interpret Ng as G times G times G, n number of G's. If n is a positive integer, and if n is 0, then this by definition is the identity element of G, and if n is negative, then this means G inverse times G inverse times G inverse, how many G inverses? Minus n number of G inverses. So this is just nothing but this integral power of G in this group, and this notation just simply indicates the fact that G is an abelian group. It will be abelian because we are having an onto homomorphism from this into G. Okay. Do you see why this is abelian? Why G should be abelian? It's not given that G is abelian. In fact, all we have assumed is that there is such an onto homomorphism. Because of this ontoness, this image is equal to G. And since f is a homomorphism, so the abelian nature of Z is carried by f to G, to the entirety of G because of this. So that's why G is abelian, and as such Ng actually means the integral power of G, where the exponent is n. So that means what? That means we have shown that this arbitrary element h of g is in fact a power of g. Arbitrary element h of g means of capital G is a power of small g. Hence, G is the cyclic group generated by this G. So that means it's a cyclic group. Conversely, let G be a cyclic group with generator. You can take again G. This G has nothing to do with that G because that is a different proof. Different proof means it's the proof of another part and it has nothing to do with this part. Okay, it's the converse of that. Now we need to show that there is one such function which is onto and is a homomorphism. So define, if you want you can call this function also f, but let's just give it another name, say k. From the group of additive group of integers to G by this formula. K of n is equal to the nth power of G. Note that now also, now we do not know if, we do know that G is abelian, right, because it's a cyclic group. So if you want, you can write ng here, but let's just write G to the power n because there is no harm in doing so. Although G is abelian, we can continue to use multiplicative notation in writing products in the group G. If you want, you can write additive notation, nothing will change. Just you have to keep in mind that whatever you are doing with the notation, that should make sense. Now we have to show two things. One of them is that K is a homomorphism and then K is onto. Okay. Ontoness is almost obvious. So let's first show that itself. It's of course obvious that this function K is well defined. Means that for any given integer n, there exists a unique image in G under K of n. So that is obvious. So let's now show ontoness of K. What shall we do? Let's take x. Let x be any element in G. Then, since G is cyclic with small g as a generator, so x will be some nth power of G for some integer n, but this implies that x is the K image of n. Hence, K is onto. Now let's show that K is a homomorphism. For any two integers not necessarily distinct n and m, we have K of you take the product of n and m in this group, but in this group the binary operation is addition, so the product is actually n plus n. This by definition is this. Now you use one of the rules of exponents which we have in every group. So by that rule, you know which rule, you have this. But this is just k of n times k of n. Times means here we have the binary operation in the group G, capital G, which we are not writing anything for that. So that's it. It shows that K respects the operations in the groups. Hence, K is a homomorphism, and we have already shown that K is onto, so that's it. This is the solution. So let's now see the next one. The next one is 29. Let n be a normal subgroup of G. Normal subgroup of a group G. Show that there exists the group H. And a homomorphism alpha of G to H whose kernel is that normal subgroup N with kernel N. And for H we are going to choose, of course, the factor group of G by N. So let's see the solution. Consider the map or function or mapping, anything you can call it, F. Oh, okay. Already we are given that the mapping is going to be called alpha, right? Alpha from G to the factor group G by N, and the definition is this: alpha of G is defined to be equal to the coset Gn of n given by the element G. Clearly, alpha is a well-defined map. Why? Because for any given input G, which is an element in G, the coset Gn is a unique coset of n, and so it will belong to the factor group. So now what is it that we have to show? We have to show Well, the exercise doesn't mention anything about this function being onto or what. No, just a homomorphism. Actually, it will be onto, but that is not asked here. So we just have to show that this alpha is a homomorphism and its kernel is going to be n. So let's just go for that. Now, first we show that it's a homomorphism, because otherwise there is no question of kernel. So to show that it's homomorphism, let's take two elements in the domain group. For G1 and G2 in N, we have alpha of G1, G2. By definition of alpha, this is G1, G2, N. But we know from properties of normal subgroups that G1, G2, N is actually also G1, N, G2, N. Well, you can view it in two different ways. They are ultimately going to be the same. You can just think of this product by definition to be this, which is in fact the definition of the binary operation in this group, factor group. That way you can view this product, or you can actually view this product in a slightly different way, superficially different but ultimately the same. You see, this is after all a group, right? So in this group we are considering these two elements, G1n and G2n, and these two elements are after all subsets of G. Now in G you can in fact consider any two subsets, A and B, and you can consider their product, AB. By definition, that product is just this. It is the set of all elements of the form AB where A is coming from A and B is coming from B. You can interpret this product in that way also, this way also. Then properties of normal subgroups, that is the fact that N is normal, gives us this as a result. Okay, then it turns out that this, if you calculate this by this rule, it turns out that that becomes equal to this. So that way also you can interpret this. Okay, there are two different ways, but ultimately we get the same thing. So that's why I said from properties of normal subgroups you get this. But then this is just alpha of G1 times alpha of G2. Here, in between these two things, we are of course not writing any symbol, but there we have the binary operation of the factor group G by N, which is just this. Hence, alpha is a homomorphism. Okay, now we come to the question of calculating the kernel of alpha. By definition, the kernel of alpha is precisely the set of those elements in G that are mapped onto the identity element in G by N. And the identity element in G by N is the normal subgroup N, because that is also a coset of N. So let G belong, I forgot how exactly we are denoting the kernel. I think it's like this, kernel of alpha. I am not sure, but by this I mean kernel of the homomorphism alpha. Okay, so let me just use this notation. So I am taking an arbitrary element G in the kernel of alpha. Then, because it belongs to the kernel, its alpha image will be equal to the identity of this group N. But also, by the definition of alpha itself, the alpha image is in fact the coset Gn, which implies that G belongs to N. Why? Because in the coset Gn, what are the types of elements? The elements look like this, Gn, where n is coming from N, all such elements. In particular, you can take the identity element in place of N here, because capital N is a subgroup, a normal subgroup, but a subgroup after all. So it will have the identity element, so that if you take here, you are getting G. So G actually belongs to this coset Gn. So that's why it has to belong to N also. So what have we ended up proving? That any element of the kernel is also in N. That is, the kernel of alpha is a subset of N. So let's conclude that. Thus, the kernel of alpha is a subset of N. Conversely, let N be any element of N. Now we want to prove that the reverse inclusion is also true, namely that N is also a subset of the kernel, and that way they will be equal. Then let's look at the alpha image of N. By definition it's N, but since N belongs to N, this is equal to N. These are properties of subgroups that we already know. And so, since the alpha image of N has been the identity of G by N, so N belongs to the kernel of alpha. Therefore, N is also a subset of the kernel. Hence, the kernel of alpha is N. So that means the group capital H that the author is asking for is actually, it can be taken, you can take G by N in place of H and alpha as this homomorphism. So this map turns out to be a homomorphism whose kernel is N. So that's what we wanted. So that is the solution, and there is one more. Let G be the multiplicative group of non-zero complex numbers. And H be the multiplicative group of non-zero real numbers. Because we want groups, so we have to remove 0 from these systems so that inverses exist. Non-zero real numbers. Then, does there exist a one-to-one homomorphism from G to H? This one is quite interesting. Interesting because it is something that we understand, but at the same time, once you suddenly look at it, the solution is not apparent. It takes some time to think about it and then come up with something. So what we are going to do is, let us take an arbitrary homomorphism, okay, alpha from G to H, and then try to gauge if that homomorphism can be one-to-one. Okay, let's try to do that. Suppose alpha from G to H is a homomorphism. Okay. Now let Z be a complex cube root of unity. We know from our knowledge of complex numbers that there are exactly 3 complex cube roots of unity, and I say complex because see, cube roots of unity come from what? It comes from this equation, right? The solutions to this equation are called cube roots of unity. Now we know that there are precisely 3 complex numbers that satisfy this equation. One of them is 1 and the other 2 are non-real complex numbers, omega and omega squared. These are things you already know. I say complex explicitly because maybe in some other field this equation has roots other than 1. So that's why I am saying complex. Okay. i.e. 1 or omega squared. Not writing what omega is, that complex number involving root 3 divided by 2, that thing. Okay, you already know that. Then let us calculate the cube of f of z. All right. What is O? This is not f. What the hell? This is alpha. Let us try to calculate the cube of alpha of z. In order to be precise, let me write like this. Okay, cube of alpha of z. Z may be a non-real complex number, that is z may be omega or omega square, but alpha of z will lie here, which is the group of non-zero real numbers. So alpha of z is real, keep that in mind. And we are calculating the cube of alpha of z. Because alpha is a homomorphism from a multiplicative group to another multiplicative group, this is equal to alpha of z cube. Naturally, because alpha is a homomorphism. But because z is the cube root of unity, this is 1. Z cube is 1. And now, since alpha is a homomorphism, it has to map the identity element of the domain group to the identity element of the codomain group. And that identity element in both of them is 1. So we have 1 here. So alpha of 1 should also be equal to 1. So that means the cube of this real number is 1. So that means this real number is also a cube root of unity. But we know that there is precisely one real number which is a cube root of unity. And that real number is 1, because these other two cube roots of unity are non-real complex numbers. So since alpha of z belongs to H, we must have this. And this we have concluded without looking at exactly what z is, that is exactly which of these values z takes. It can either be 1 or omega square, it does not matter. We are ultimately getting this. Thus, alpha of 1 is equal to 1, which is something we already know since alpha is a homomorphism. But at the same time, alpha of omega is also equal to 1, and alpha of omega square is also equal to 1. Although we do not need to write this many things, but still. And since 1 omega square are all distinct, these are 3 distinct complex numbers. Alpha is not 1 to 1. So that means no homomorphism from G to H can be 1 to 1. Okay, so it's impossible to find such a homomorphism. There does not exist such a 1 to 1 homomorphism from G to H. I think it would be better if you write what omega is. You just here, instead of writing these things within brackets, you just write i.e. z is 1 or omega square, where omega is this complex number, that you write. Okay, and that is the solution. So this set of exercises is over. So in the next Lee update, we are going to see what comes next. And that's just it for tonight. And tomorrow we have our usual calculus, not calculus, but analysis video. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Group. Have a nice night.